Today we are discussing about generation of amplitude modulated double sideband suppressed carrier. So in the previous classes we derived the equation for DSBSC. So we can achieve 66.7% of efficiency when compared with double sideband full carrier AM. So now how to generate DSBSC AM. So with help of these two methods we can generate it. One is balanced modulator method, second one is ring modulator method. First, balanced modulator method. So the same circuit can be used to generate AM with carrier. The main difference between AM carrier generation and DSBSC AM is the feeding points of the carrier and modulating signals are interchanged. So in AM, here in the primary we applied VC, and in the secondary coil near the emitter terminal we applied VM. Here it is reversed, so that is the only difference. The operation is quite similar. The transistor is operated in a balanced mode, thus heavy filtering is not required to remove the unwanted harmonics. That is the main advantage of this balanced modulator method. So the circuit itself, it is balanced with respect to the center tapping. It is assumed that the two transistors are identical and the circuit is symmetrical. The operation is confined in the nonlinear region of the active devices employed in the circuit. The carrier voltage across the upper and lower part of the secondary windings of the center tapped transformers are equal in magnitude and opposite in direction. So there is a difference in the current direction only. Everything same. In the principle of operation, the modulating signal is applied to the input of the transistor T1 and T2, and the carrier signal is applied to the common input to the push-pull amplifier configuration. Because of center tapped transformer are equal and opposite in phase, VM is equal to minus VM. That is, upper half is VM, the lower half is equivalent to minus VM. So the input to the transistor T1 is given by VBE, EM of T and EC of T. So EM of T is modulating signal, EC of T is nothing but carrier signal. So substitute those values, we get VBE. Similarly, VBE dash, according to this transistor T2, the only thing is the magnitude of EM is reversed. So minus EM of T plus EC of T. So substitute the modulating signal value and carrier signal value, we get this value. And by using the nonlinearity property, the collector current can be written as square law equation. So that is IC is equal to A1 into VBE, A2 into VBE square, and so on. Then IC dash, due to the second half, A1 VBE plus A2 VBE dash the whole square. And substituting all the values in IC and IC dash, we get this equation. So the output AM voltage is given by V0 is equal to some constant value into the change in the or difference in the current across the secondary coil. So that is V0 is equal to K into IC minus IC dash. So we have the values for IC and IC dash substituted from the previous equations. We get V0 is equal to 4K into EM EC sin omega MT into omega CT. When you expand the sin A sin B, we will get cos A minus B minus cos A plus B divided by 2. So that is the relation. Here you have to notice that there is no carrier frequency. Only the frequencies are related with sideband frequencies alone. So we can say that on sideband frequencies are available. Only the carrier frequency omega C is suppressed. Only the sidebands are present in the output. Hence the DSBSC AM generated at the output. The main advantage of this modulator is saving power and efficiency because of the suppressing of carrier. This is one method of generating DSBSC. The next method is ring modulator method. The balanced ring modulator circuit is widely used in carrier telephony, suppresses both unwanted modulating and carrier signal in its output. So that is the main advantage of ring modulator. So practically we are using ring modulator type when compared with other methods. The band pass filter is not used at the output, hence the harmonic frequencies are automatically controlled by itself. In a ring modulator circuit, 4 diodes are connected in the form of ring in which all the 4 diodes are connected in the same manner and they are controlled by a square wave carrier signal EC of t. The carrier signal acts as a switching signal to the alternate polarity of the modulating signal at the carrier frequency. When there is no modulating signal, diode D1 and D2 or D3 and D4 will conduct depending upon the polarity of the carrier signal alone. That is, we can obtain the carrier signal as it is when there is no modulating signal in the input side. Positive cycle of the carrier. Diodes D1 and D2 are forward biased. Here let us assume this is the circuit diagram for ring modulator circuit D1, D3, D2 and D4. So this D1 and D3 both are forward biased. D2 and D4 are reversed biased when the modulating signal is applied at the point A and in between B. Whereas it is reverse biased and this combination is forward biased when the modulating signal is applied across these C and B terminal. Then we'll come to the operation again. So diodes D1 and D3 are forward biased. At this time D2 and D4 are reverse biased and it acts like a open circuit. The current divides equally in the upper and lower portion of the primary winding T2. The current in the upper part of the winding produces a magnetic field that is equivalent and opposite to the magnetic field produced by the current in the lower half of the secondary. Therefore, the magnetic field cancel each other and there is no output induced in the secondary. Thus, the carrier is effectively suppressed. Similarly, the same thing applicable for negative half cycle of the carrier also. Here, the only change is the upper half cycle is reverse biased. At the same time, the lower half is forward biased. So from this operation, we can define EM of t is equal to EM sin omega mt, EC of t is equal to EC sin omega ct. So simple product modulator. So multiply these two will directly give you R VO of t. So EM EC by 2 into cos A minus B minus cos A plus B divided by 2. So there is no prominent frequency, carrier frequency in the output equation. So we can say that the carrier frequency is suppressed, only the sideband frequencies are available.